Hi, everybody. Welcome to the first Early Career Award, Early Career Spotlight talk at RSS this year. So these Early Career Spotlight talks are given by rising stars in the robotics community, and at this RSS we're going to have 3 of them, and it's my great pleasure to introduce the first speaker, Maya Cakmak. Maya got her PhD at Georgia Tech, and her research is in human-robot interaction, where she's really focusing on how we can enable non-expert end users to program robots to do useful everyday tasks, such as kind of cleaning your house. I'm sure we're all very excited about this work succeeding at some point and really getting these robots into our homes. During her PhD research, she showed also, for example, that robots can really benefit from interacting with a person. For example, when a person is trying to teach the robot or show it something by demonstrating it to the robot, then the robot can, for example, ask questions such as, in this demonstration, is it important to hold the cup upright, or is this just an artifact of the of the demonstration you're giving? So really kind of combining machine learning techniques with human-robot interaction to come up with these kind of questions for her work. She received the Best Dissertation Award at the Georgia Tech College of Computing. After that, she joined Willow Garage. I think the more senior generation here knows exactly what Willow Garage is about, but at the time she was really also motivated to learn more about what it takes for robots to operate in the real world. And then after 2 years I was also really excited that she decided to join the University of Washington in Seattle, the faculty there, and since then she's been working on, again, enabling end users to program robots to do these useful tasks. She developed a RoboFlow, which is a specific programming language that non-computer scientists could use to program robots. She received several paper awards, a career award, and also recently a Sloan Fellowship for her research. And what I find really exciting is this combination of technical work and a focus on how robots can interact with people and how they can solve like real-world tasks that we might care about. Her work has also had real-world impact on companies already. So there are several companies like the Savio hotel delivery robots or the Fetch logistic robots that use parts of Maya's work really at the core of their robot control systems. And in order to really figure out what it takes to get a robot into a home and what useful tasks there are, she actually went so far to deploy a Pier 2 robot for 1 year in a person's home in Arizona, and then try to really figure out like what it takes to succeed in such a real-world setting rather than just the laboratory settings. So with that, without further ado, Maya Cakmak.
All right, thanks, Dieter. Lots of spoilers in there. So let me start by saying this has been a very inspirational conference so far. I'm really honored to have the opportunity to talk about my research. And also, I would love to have a picture of this. So if you have a camera and would like to talk to me afterwards, please take a nice picture of me when I'm like really passionate. So like many roboticists, my work is motivated by the vision of robots doing useful things for people. And personally for myself, I'd like to have robots do many of the house chores by the time I retire. So I have to match the decrease in my capabilities with the decrease in my robot's capabilities. And we're clearly making progress towards that. So most of you have probably seen a video of a robot like the PR2 doing something quote unquote useful, like I don't know, fetching a drink, beer from the fridge, maybe putting dishes in the dishwasher, scooping dog poop, etc. So there is evidence that things like this are actually possible under certain circumstances. So why aren't they in our homes yet? Among many practical problems, Chad pointed out some of them, like price points, I believe we have 2 really important key problems. The first one is that most of these really impressive demos are actually tailored to a particular environment. So you take them out of the lab, you bring them to your kitchen, it's not going to work. So think about, for instance, Amazon Picking Challenge entries, how those would work in your pantry. Secondly, even for this very tailored solution that might work very robustly in one environment, you require very highly skilled engineers to work very long development cycles. So it takes a lot of time. Again, think about preparing for an Amazon Picking Challenge. So most robotics research actually targets the first problem. So we try to build universal capabilities, like perception and grasping, things like that, that would basically work in every possible scenario. So think about robots that can do everything in every possible environment. That's kind of the holy grail. And we're actually making great strides. Again, think about perception, grasping, but we're still far from practicality with this. So instead, in my research, I say, let's embrace the tailoring to the environment. After all, my robot is not going to go to all different homes. It just needs to work in my home. So if I had a team of engineers just work for me, they could make it work for me, right? The issue there, the scalability issue, is that we don't have a team of engineers for every home. So we have a different challenge. Basically, we want to make it possible for everyday users who will get these robots and will be the main users of them to be able to program the robots for themselves. Okay, so robot programming is actually as old as robotics, but surprisingly, not much has changed. So there's this awesome paper by Tomás Lozano Pérez, which was published the year I was born. We reference it a lot in my lab. We call it the TLP paper. And it's mainly focused on programming of industrial robots. But actually, it's spot on about what is unique about programming robots and what the requirements are for being able to program robots. So basically, we have some great foundations, but we're trying to expand the notion of what a robot programmer is. So today, many robots are programmed with tools like ROS. It's pretty amazing that you can just download these and start programming. This is a lot of progress in this space, but ROS programmers are still pretty small population. So it takes several weeks to learn ROS, and that's already if you're very good with C++, Python, etc. And we want to expand this to a much broader group. So think about grandma in the home to maybe like a professional developer who's not a roboticist, works at a robotics startup, or somebody who's trained for about a week to do robot deployment. So this is a big spectrum of end users that we're targeting. So a lot of the inspiration for our end user tools actually come from the tools we built for ourselves when we were programming robots. So one unique experience Dieter mentioned, in 2014, we actually deployed a PR2 in a private estate in Arizona. This is a very long story how we got this gig. I'd be happy to tell you later. But we had many challenges that were non-research, like how to talk to eccentric millionaires or how to install a ramp to the kitchen, things like that. But we actually learned a lot as well. So we were mainly hired to develop robot apps for the owner. And one of the first things we did was talk to him about what he imagined as having as apps on his robot. And of course, we had to shut down some of the crazy ideas, but we were able to agree on a set of 17 apps. We had those kind of referencing all the time. And we could say, yes, these are actually possible with the PR2, and we could deliver this within reasonable time. These are things like carrying packages from the door to the office or fetching a drink. He liked Red Bull from the kitchen. And these are end-to-end applications that require expertise in things like manipulation, perception, navigation, etc. And building them would take about something like a month. But thinking about many apps simultaneously actually allowed us to see some common patterns. So things that would be usable across programs and repeated processes that we were doing very inefficiently. So invested time to actually build these tools for ourselves with the hope that it would make us much more efficient, but also ultimately the user could program their robot. So one of the key questions we need to answer to get people like our PR2 user to program robots like PR2 is what is the underlying programming language that they're communicating with the robot, and what is the right interface for programming with that language? And obviously the answer is actually different for programming robots at different levels, right? As well as for different types of end users. And oftentimes, we have to find a trade-off between expressivity and intuitiveness of the tools. So to that end, our work does a lot of interface design, inventing new ways to program robots or communicate with robots, but also choosing the right representations and developing new capabilities to provide those interfaces, and sometimes putting our tools to test with real people to validate them and learn ways to improve them. Okay, so what I'd like to do is go through and introduce some of these tools. And I won't have enough time for details, but I will try to give some of the key insights about them and some observations we've made over the years. As I mentioned, robots can be programmed at different levels, and the TLP paper actually gives us a good way of categorizing those. So we have perceptual capabilities, actions like manipulating things, and also high-level tasks where we combine these things for something like organizing your kitchen. And many of our tools fall under one of these, but to do end-to-end programming, to really deliver an app, we need a suite of these different tools. So let's start with something simple. Many of you probably have heard of programming by demonstration or learning from demonstration, if not Chad's talk yesterday. So this is one excellent interface for that is kinesthetic teaching, where the user guides the robot through, as in this example. And there's a lot of research in this area with very impressive results. But one of the issues has been that this hasn't been considered as an end-user tool. So their evaluations often involve people who know exactly how the system works, actually programming the system. And this goes, a lot of my thesis work was showing that there are many assumptions that are violated by users and trying to come up with solutions for that. So think about something simple like stacking 3 cups. So many of our existing methods are data-driven, so you need multiple demonstrations. Already at that point, you're losing a lot of users because you can imagine how demonstrating something like this 10 times gets really boring. People, even if they're willing to demonstrate, they're also not good at picking demonstrations such that they span the state space and allow for correct generalizations. And third, it's hard to know when you're done because these are black boxes, so we have to actually test them. So people who are bad at giving examples are also bad at testing these systems. And this includes myself. So the only way I got good at using these was really understand what the underlying representation was and be able to inspect what was learned from the examples I was providing. So in this work, which we presented at RSS a few years ago, we wanted to give some type of transparency, just like I had when I could understand what was going on underneath. And we wanted to use visualization for this. So for this, we needed a very simple representation that would capture some useful task, but was also visualizable and people would understand. So here, this basically represent actions as a sequence of poses that can either be relative to the robot or relative to landmarks in the environment. And this was taken from the literature, where basically the previous work was to learn how poses are assigned to different landmarks in the environment from multiple demonstrations based on the regularities across demonstrations. And that's exactly where it went wrong. So what we did instead was, from a single demonstration, use a very simple heuristic to assign poses to landmarks, basically based on proximity, but then let the user correct if there were any mistakes. So people could just see their mistakes and be able to correct them directly by editing the visualization. All right, and I'll just skip here, but one of the points here was that even though this was very simple, it worked really well with people, we could still capture quite a few types of tasks like assembly, changing state of objects, multi-object organization, disassembly, etc., coordination of 2 arms. Okay. And the task can get arbitrarily long with this representation, but we quickly hit a wall in terms of expressing some kind of logic. So something like stacking 3 cups only works when there are 3 cups, whereas it should actually be really easy to say stack and cups or stack all cups. So for this, we started looking into more expressive representations, and indeed, research in learning from demonstration started moving towards that as well. But again, it suffered from the same problem of requiring the right set of demonstrations to learn the right representation. So again, we tried to bring this same idea of what I call initialization by demonstration, where you provide one demonstration of something like stacking, and then that synthesizes automatically a very simple program. Basically, from one demonstration, you can't do much. But then, instead of trying to provide more demonstrations, the user directly edits the program that was synthesized. And this can allow things like having loops, where you can adapt based on the different numbers of objects, or have things like error recovery built in. When one thing doesn't work, you try something else. Or you have actions that behave differently in different situations. Like if an object is too far, it's pushed towards the other hand. But if it's already at the right side, it's directly grasped. So we got a lot of power just from adding loops and conditionals into the representation, but that's still not a general purpose language where you can have something like variables to maintain and manipulate state. And we realize even children are programming their toy robots with those types of languages. So the secret of those is that they basically use visual interfaces that remove the need to memorize syntax for knowing a language, and make it much more difficult to make simple mistakes when you're programming. So we took one of those interfaces, this one is called Blockly, and started thinking about what would be the right type of blocks to have if we were programming a real robot, a non-toy robot, like our PR2, with this interface. And of course, we could provide simple things like asking questions on a screen, etc. But one of the immediate ideas was to integrate this with programming by demonstration. So basically, things programmed at the low level, you give it a name, and now it becomes available as a block you can have at the high level. And you can still have a lot of the logic around branching or parameterizing the action, or things like looping at that high level. So here's an example of an action you can program like this. So this is in the context of Amazon Picking Challenge, where the robot targets the crayon box and detects if it's graspable. And if not, it goes and picks this tool that's on itself and tries to make the object graspable, and then eventually goes and grasps it. So this is also with the integration of perception at the high-level programming. Now, the way perception is integrated into high-level programming is through simple call, like detect landmarks, parameterized by some kind of known landmark type, like shelf edge or crayon box. But again, you can see that there might be many matches for certain types of landmarks, and this kind of demonstrates the powerful use of high-level programming to figure out, use logic and math to figure out which one of those should the robot be pulling the object relative to. Now, let's talk a bit about programming of perceptual capabilities. So manipulation requires perception, and many of our systems have some form of built-in perception, whether it's a generic landmark detector with some descriptor, or some kind of object-specific, task-specific object detector with a large repository of objects. Unfortunately, you don't find things like shelf edge, which might actually be really important for your task in these kinds of repositories, right? So as we were building more and more applications, we kept running into the limits of our perception system and had to come up with these custom, shelf edge detectors. So this led to development of some new tools for customizing the perception. So this is basically giving examples of what are landmarks in the environment that are relevant for the task that's being demonstrated directly by the user. So things like the shelf edge that I just showed, something like a drawer handle, examples here, bowl rim instead of the whole bowl so that you can grab it from the rim, etc. And specifying landmarks with a single example, so this is one shot, and required some technical capabilities to localize them in new scenes, right? So I won't go into detail. It's basically a modified ICP algorithm. But one of the key things that made it work was to explicitly represent empty space. So basically, you had a good match if the empty part of the landmark matched the scene. And in turn, this allowed us to do something we didn't expect to be able to do with this, which is represent emptiness constraints for tasks. So things like being able to detect an empty box, or find a large enough empty patch on a table, or see if some cloth was successfully lifted by matching the empty or the non-match of an empty hand, etc. And this is all built into the perception system. And this ability was basically allowed us to be able to program capabilities like picking up a bowl from the rim, or something like pushing a chair without having to model the whole chair. So I've shown one set of tools that allow kind of end-to-end programming. And we actually have a lot more tools. Some of them we have already abandoned. Others are currently half-baked, et cetera. So it's a constantly growing list. But many of these tools actually have similar underlying representations, and we can sort of program the same thing through different interfaces. So I want to highlight a couple more of these to demonstrate how we obtain similar robotic capabilities from very different interfaces. So one of these tools targets the challenge of referencing the environment when you're programming. So think about you're sitting in front of a screen and you have to tell the robot to pick up something, reference that object, or place it at a particular location. So that's really hard when you're not situated in the robot's workspace. So the idea here was to have these tangible tags that had a meaning for the robot to basically program the robot. And the key elements here were what we call selector tags that could select an object or group of objects or define a location or a region. And then you could attach actions to them and you could order those actions in particular ways. So basically program the robot, tell it what to do just by putting these things in its workspace. And you could further extend this by having some kind of projections. So having the robot actually give situated feedback. So here's another example. This is an alternative for providing demonstrations. So this is from a collaboration with Dieter's lab, where we basically use robust hand detection, skeleton tracking, and object tracking to try to provide a demonstration of a task to the robot. So this has been something we've done for many years, but mostly with motion capture. So thanks to things like Dieter's perception systems, we can actually do these things now. But there are still a lot of challenges, like once given this rich information, the robot needs to come up with something that's executable, and that involves things like detecting contacts, or which of those contacts are grasps, things like segmenting it, transferring the grasp, while thinking about all parts of, or important parts of the trajectory still being reachable for the robot. And you can program a lot of the things we do with other tools with this, but here I have, here I had two that were kind of things we can't really do, something like jiggle it out that you can demonstrate, but it's much harder with some of the other tools. Okay, so those are some of our tools. Now let me spend a few minutes to talk about some observations from these tools that we've had over the years. So one of the most common themes that I've seen is that people prefer things people prefer and are better at using dumb tools that are very interpretable for them, instead of things that might be very impressive and look smart in certain situations, but then fail in ways they don't understand. Okay, so for example, in this study where we had the user sort of specify the sequence of poses to go through, it was actually better to have the robot go from pose to pose on a straight line than try to do obstacle avoidance, because if the robot hallucinated some kind of obstacle and did something they didn't understand, they didn't like it. And most people first made the mistake of making the robot collide into something, but they quickly recovered from this. So it only happened once, basically. People were good at providing these waypoints to fix that. Second important point, which I've already raised, is we have a spectrum of end users. And this is not just across different tools, that one tool is for one user, one for the other, but also in terms of the use of specific tools. So for example, I was the only one at Willow Garage. I was the only one at Willow Garage who was able to teach the PR2 with this very simple system to do this Japanese t-shirt folding. And I could do it repeatedly. So you can sort of see that getting much more practice with the system actually increases the capabilities of the system for that user. The distinction between novice and expert users comes up a lot. For example, even though novices were as good as experts in obtaining generalizable tasks, correct tasks that worked, they took a lot more time to do that. That was one difference. And also subjectively, people with different backgrounds have different reactions to our system. So for instance, in this study, we had different types of users, and someone who's like a programming language expert would say, I hate visual programming. Roboticists said things like, said the same thing basically in a more gentle way, I'd rather use Python. But actually, somebody who was a non-programmer, arguably the exact target group for this tool, said they liked it for the exact reasons visual programming is powerful. So for tools targeted at different users, one of the key differences is usually training time. So for instance, training for the combination of tools that allowed end-to-end programming required 1.5 hour training. This was across multiple sessions to start actually being able to program the robot. Whereas for situated tangible programming, people were already pretty successful without any instruction whatsoever. So we give them the tags, some things are written on the tags, and it's self-explanatory. And just redesigning the tags made this even better, and just 5 minutes of instruction, people almost removed all their mistakes when they were interpreting programs or building programs themselves from scratch. But I think even 1.5 hours is actually pretty impressive. To put that in more absolute context, look at sort of the number of pages of these user manuals for industrial robots, that some of which are specifically designed to be easy to program and advertise that way. So even just reading these would take more than some of our longest trainings for our tools. And I think, and the complexity, some of these user manuals actually have things like, matrix transformations and kinematics, et cetera. Similarly, here's an example to put the programming time in context a little bit, although these might not be super fair comparisons. For instance, the crayon box example was something we did during the summer, following Amazon Picking Challenge. So it was an intern project, and 3 programmers worked for about 16 weeks to obtain. This was one of the actions, so there were other ones, but that's kind of the Ross way. Versus my student took 2.5 hours to program the same thing using this combination of tools. Similarly, a 10-week project from my class could be replicated within 3.5 hours. Okay, so one of my favorite results is that these tools actually really allow the users to demonstrate their creativity, to find different solutions to similar problems. So this is, let's see. Okay. So this is the towel folding task, and you can kind of see all the variations of people folding the same, sort of obtaining the same result in different ways. And also an example here from the situated tangible programming, where they basically have pretty different programs that achieve the same thing. All right. Now, these are some of the observations from studies that we do in the lab. There's some value to that, but some of our most important learning, actually, sometimes through failures, is through real deployments of these tools. So some of our projects were actually motivated by the Savio QSK. So Savio has this hotel delivery robot, and that was their one use case, and they delivered this. They started getting requests from the hotels for slight modifications, like could it say happy birthday if it's somebody's birthday, or new applications. They see what the robot is capable of, and they get new ideas of things the robot could do for them. But this was basically, Savio could not handle this with their regular development process. So 2 of my students interned there to build similar tools for them. And now Savio has actually a customer representative who's not a programmer that goes to hotels, whether it's like current existing customers or potential customers where they're trying to make a sale, and be able to program the robot on the spot based on their requests. Savio also uses these tools for customizing behaviors, for instance, at trade shows or testing internally. It has made them faster as well, and also exploring new applications as kind of a fast prototyping tool. So finally, another way we constantly put our tools to test is through outreach. This is a perfect match, making it easy to program and outreach. So I have a demo in my lab almost every week, and it never gets boring because it's different every time. The person who's visiting gets to decide what to program. But one particular event has been really informative, especially in terms of accessibility of our tools. So this is the 1-week robot programming workshop that I've been running for the last 3 years, where the students basically use our tools, learn to use our tools. And these are some of the things that you saw in the video that they were able to program. And these are non-programmers that just learn to program and learn to use our tools at the same time. Okay. So to wrap things up, I motivated my work as kind of a pragmatic alternative to developing universal capabilities. But I think one of the more important impacts of this work will be the democratization of robots, right? So to enable new applications that roboticists would never have thought about. So because, for instance, with all my privilege, the thing that I want from robots is cleaning my house. And if I hadn't met Henry Evans, I would never have known that something like scratching your face or wiping your face is an app that should be on a robot. And in turn, Henry couldn't have done this without Charlie Kemp. And we don't have a Charlie Kemp for the millions of users who are living with a disability. So hopefully, these types of tools really enable people to develop robots that are actually useful for what their specific needs are. OK, so with that, let me thank all my wonderful students who do the harder part of all this work, and NSF for all the funding. And here are some of the key references of the papers that I presented today. Thank you.
Time for a few questions. Oh, there's a question up there. On the microphone.
Thank you, Maya, for this talk. Have you been trying to play with language, verbal commands at all?
Sorry, could you repeat the question?
Yeah, sorry. You've been mostly showing us interfaces that are built on graphical blocks or things like that. Have you been playing with using verbal interactions from the users?
Yes, yes. So I had to cut back on the tools that I present, but verbal definitely is a great fit for high-level programming where you're describing the logic of the task. But also, we've even done work where we try to model the prepositions of how motion is relative to objects in the environment. So even try to create a hands-free programming by demonstration by describing some kind of motion, like move towards the object, move upwards, etc. So yes, definitely.
So orange cube.
Wow, what's next?
OK, good question. So one of the things that's actually started with Savio was that even though the robot is built for something very functional, and they had the numbers right that it would do this many deliveries and the staff hours would go down, etc. The biggest value that hotels found from having the robot was the social interaction. So people actually wanted deliveries just to interact with the robot, and the hotel started asking for things like, can the robot mingle in the lobby? Can it deliver things in the lunchroom, etc. So that made us realize that a lot of our tools are actually not very good for social interaction. So one of the really simple things, for instance, was handling concurrency. So we wanted the robot to be able to go somewhere while being able to stop if something happens on the screen. And like concurrency is, it's really hard for programmers even. So Ross has all these fancy things. But how do we make that possible for end users? So that's been one of the challenges. And then, again, going more towards social robots. So there are many existing social robot platforms. These could be used for many different applications. Again, I'm part of one project, but I keep getting requests for being on other projects, and I can't build so many robots, but I can build these tools such that psychologists or social scientists, et cetera, who have these ideas can build their own robots for those applications.
Question with the green one, or blue? Blue.
Programmers don't like the visual programming paradigm. I'm wondering about the reasons there, but also have you sort of ran into limitations of visual programming, and what is the biggest limitation that you see there in terms of visual?
Yeah. So it's definitely not a silver bullet. So even though it simplifies and has these advantages over written programming, it can get very complex. So some of the programs of the tasks you saw, they're actually huge. If you zoom out, it's like you can't really see what the lines are. So it gets pretty complex. That's one big limitation. Again, now we're experimenting with having concurrency, whether it should be visual. There is a nice thing about parallelism kind of representing concurrency, possibly. But again, the biggest thing is scalability. So the programs have to remain not so complex. And with concurrency, we could easily get very complex. So yeah.
All right, let's thank Maya again.